Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 53. It's on rotational motion, which is turning motion. And that would be dangerous if you're a slackliner like this person in Yosemite. As he applies a force or a net torque on one side, you're going to get rotation, which he has to counteract with a net torque in the other direction. And so by moving your arms out, you can increase your inertia, but it still is difficult, and that's why he's attached on here with a rope. And so if we take an object and apply a net torque to it, what we get is rotational motion. We measure that in physics according to its angular displacement, so the angle at which it's turning, its angular velocity, so the speed at which it's turning, and then the angular acceleration, which is how much that angular velocity is increasing or decreasing over time. Now the whole object has the same, for example, angular velocity. But if you look at different distances out from the axis of rotation, obviously out here it's going to be going faster than it is in here. And so all we do, for example, is take the angular velocity times the radius, or the distance from the center, and that's going to give us its linear velocity, or its speed in that one direction. Now another term that you should understand is rotational inertia. And so we know in regular physics that force is equal to mass times acceleration. If we apply a force times a mass, we're going to get an acceleration. Now in rotational motion, the equation looks a little bit different. If we apply a net torque, so if we're applying a force, remember, that is perpendicular to the lever arm, if we apply a net torque, that's going to be equal to the rotational inertia. In other words, that's how much this object resists change, or resists that change in motion, times the angular acceleration. And so a good understanding of rotational inertia is important when you're trying to solve problems like this. Before we get to that, we have to understand the importance of the radian, because that's the base unit when we're measuring angular velocity, for example, or angular acceleration. So if I draw a radius like this, and then I take that distance of the radius and wrap it around the circle, I now have the angle of 1 radian. And so this would be 1 radian, 2 radians, 3 radians. This would be pi radians, 180 degrees or half a revolution. Or if we go all the way around, that's 2 pi radians. And so you should understand what a radian is. It's about 57 degrees, but also it's the base unit as we're measuring this rotational motion. And in the back of your mind, you should know that 1 revolution equals 360 degrees equals 2 pi radians. And so for measuring angular displacement, we measure that using the angle theta. So it's going to be how much it's turning, or the distance by which it's turning. And so again, we would measure that in radians. And this is 1 radian right here. It's about 57 degrees. What's angular velocity then? Angular velocity, and we use the symbol omega to represent that, is simply the change in that angle over the change in time. So let me animate this for a second. We're going to move that 1 radian in 1 second. And so what would our angular velocity be? It would be 1 radian per second. And so it's how fast this thing is turning. So if it took 1 second to go all the way around, then it's going 2 pi r, or 2 pi radians rather, per second. Now let's do an angular acceleration. So what is that? It's the change in angular velocity over time, or the change in omega over time. So let me start the spinning. At the beginning it has an angular velocity of 0. But after 5 seconds, let's say it's going at 1 radian per second. So how would I figure out my angular acceleration? It's going to be the change in omega, which it went from 0 to 1 radian per second. So that's going to be 1 radian per second. How long did it take to do that? It took 5 seconds. And so my angular acceleration would be 1/5, or 0.2 radians per second squared. Now let's do some simple problems. And I'm using an album of mine. Of course, it's Pink Floyd's Dark Side of the Moon. You can see I have to clean up the album a little bit. But let's say that I start it spinning like this. And it takes about 2.8 seconds for this to get up to speed, and then it spins at 33.3 revolutions per minute. Well, you can see right away that this revolutions per minute is how much it's rotating in a given period of time, and so we're already halfway there when we're trying to figure out the angular velocity. Angular velocity, remember, is equal to the change in theta, so the change or in angle over the change in time. And so if I start solving this, what's my change in angle? Well, I said it's 33.3 revolutions per 1 minute. Now, these units are bad. We have to get this to radians and we have to get this to seconds. And so we can just do some factor label. I know that 1 revolution equals 2 pi radians. And so right now my revolutions cancel. And I know that 1 minute is equal to 60 seconds, so my minutes cancel. And so if I calculate that out, it's going at about 3.49 radians per second. which makes sense. If it takes a minute to go around 30 times, it makes sense that it's going a little more than pi radians, or 3.49 radians per second. So that's my angular velocity, and it's the same for any point along that album. Let's say I want to figure out my angular acceleration. Now, how do I do that? What do you need to do? Well, I'm giving you the time at which it's changing, and so it's changed, or my change in omega is going to be 3.49 radians per second, and it took 2.8 seconds to get up to that. It started at 0 and it got up to that speed after 2.80 seconds, and so I'm going to get an acceleration of 1.25 radians per second squared. So that's how I calculate that. Now, one thing you should understand is that even though this whole album has an angular velocity of 3.49 seconds, not every point along that album is going at that same linear speed. And so we have an equation for that as well. It's called linear velocity. And that's simply equal to omega, or angular velocity, times the radius. And so if we do a point right here in the middle, let's say that's 0 centimeters from the center, so it's right at the center. Well, there's one problem here. This should be converted, but I don't have to because it's just 0. So if I take my angular velocity of 3.49 radians per second times 0, what's my velocity? 0. And so its linear velocity is 0 at the center. What would it be as we move farther out? So let's say out here, since this is a regular album, it's 6 inches out here, or 15.3 centimeters. So if I want to calculate that, I'm going to say my velocity equals to omega times radius. What's my omega? 3.49 radians per second. What's my radius? It's 0.153 meters. I've converted that from centimeters to meters. And so what's my linear velocity? 0.534 meters per second. So it's going, a little over a mile an hour if we're going around the outside. So it seems like it's going fast, but not that fast. And now we're going to start talking about applying forces to an object and creating these motions. And so there's a nice PHET simulation. You can see that if I move it in this direction at a constant speed, I've got linear velocity. If I move it in the other direction, I've got linear velocity. Let me freeze that for just a second. And so now it's not accelerating, it's just moving with a constant angular velocity. But what you can see is the linear velocity is greater on the outside than it is as we move farther in. But also this is accelerating. Even though the velocities are constant, their direction is. And so what we have is called a centripetal acceleration to the inside. But what I'm now going to do is start applying a net torque to it. And so I'm going to start pushing and pulling on it, and what you'll see is that we'll get huge accelerations in one direction, and then as it stops, it goes back in the other direction. So as you apply a net torque to an object, we're going to get that acceleration. And so just like force is equal to mass times acceleration, in rotational motion, our torque, or that force that we're applying, is equal to not mass, but rotational inertia times its angular acceleration. And so what is rotational inertia? Again, it's the resistance to motion of an object in rotation. And so to demonstrate that, I have two pieces of PVC pipe. They're exact same mass, exact same length, and I'm going to drop them at the exact same time. And you can see that they land at the exact same time. Now what I did is I taped a weight to one of the PVC pipes, and then I'm going to drop them at the same time. So make a prediction for a second. Which one do you think is going to land first? The heavier one, the lighter one? Are they both going to land at the same time? Let's let that go. And so you can see that the lighter one hit first. Why is that? It's because it has less rotational inertia. And so as this force of gravity acts on it, it's going to turn with a lower acceleration. And so another way to look at this is a demonstration here. What I have are four objects that all have the same mass. This one right here is a solid cylinder, and this is a cylinder where all the mass is on the outside. This is a solid sphere, and this is a hollow sphere. And so which one do you think is going to make it to the bottom first if we race them and they all have the same mass? Well, this is kind of counterintuitive as well. If we let this run, you'll see that the solid cylinder gets there first. And so if we kind of pause that for a second. So this solid, rather, sphere is going to make it to the bottom first. Why is that? It's because it's going to have a lower rotational inertia. More of its mass is going to be towards the center of that object. Whereas up here, all of that mass is around the outside of the object. Now, there are going to be equations to calculate the rotational inertia of each of these, but what you should understand is that the bigger I is, the bigger that rotational inertia is, the more torque we have to apply to have a similar acceleration. And since the force is the same on all of these, the ones that have the greatest I, or rotational inertia, are going to have the slowest acceleration. And so did you learn to make predictions about velocity around an object? Again, we've got angular velocity, displacement, and acceleration. If we want to figure out linear, we have to multiply it times the radius. And then finally, could you collect data to see how a force or a torque applied to a rotating object affects its acceleration? There's a wonderful PHET simulation. I'll put a link down below, but I hope that was helpful.
JC Daen, and my topics are rotational motion and angular quantities. Rotational motion. Rotational motion is motion which follows a curved path. This is in stark contrast with linear motion which follows straight paths. We have example number 1. An object attached to a 0.5 meter string does 4 rotation in 1 second. Let's find tangential velocity of the object and angular velocity of the object. To get tangential velocity of the object, our formula is 2 times pi times f times r. Pi is equals to 3.1416, f is equals to 4, r is equals to 0.5. This is our given. Then apply the formula. V is equals to 2 times 3.1416 times 4 times 0.5. And the answer is 12.57 meter per second. Next is angular velocity of the object. This is our formula. 2 times pi times f. Our pi is 3.1416. Our f is 4. 2 times 3.1416 times 4. This is the applying formula. The answer is 25.13 radians. Next is angular quantities. The first thing you need to know about rotational motion are the 3 basic measurements. There is theta, which measures the angle, omega, which measures the angular speed, and alpha, which measures the angular acceleration. Theta, omega, and alpha are what we call angular quantities. Theta is the angle of the object. In this case, the theta happens to be 45 degrees or pi 4 radians depending on which measurement system you use. The arc length is calculated from a simple formula, and that is arc length is equals to radius times angle in radians. So the radius is pi over 4 times 16 angle in radians. This 16 is given, and pi 4 is the arc length or the theta. The radius, that is 45 degrees, but we use in radians, so that is equivalent to pi 4. Omega is the angular velocity. Each of those sections is 45 degrees or pi 4 radians, and each is covered in 0.75 seconds. So by the formula, average angular velocity is equals to change in angle over change in time. This is change in angle, pi 4 or 45 degrees, and this is the time, 0.75. Pi over 4 over 0.75 is equals to 1/3 pi per seconds. That is average angular velocity. Last is alpha. the angular acceleration. In this picture, the circle is divided into slices which are pi over 16 radians. It is equivalent to 11.25 degrees each. Were this a constant angular velocity, one slice would be covered per second. But there is an acceleration of pi over 16 per second present. Thus, first one slice is covered, then two, then three, and so on. The calculation is quite simple and analogous to regular acceleration. The formula is average angular acceleration is equals to change in angular velocity over time. Our change in angular velocity is pi over 8 minus pi over 16 because you need to put the changing velocity to get the present angular. So pi over 8 minus pi over 16 over time, that is 1 second, and that is equals to pi 16 per second.
Everyone, we're the group number 4. Our topic is about rotational motion. I'm Eldon R. Lorenzo. My topic is about conservation of angular momentum.
And I'm Jeremy Labasan. My topic is about rotational motion of an atom.
For this next lesson, my lesson is about conservation of angular momentum. First, we need to know what is conservation of angular momentum. Conservation of angular momentum is the rotation analog of linear momentum. It is an important quantity in physics because it is a conserved quantity. The angular momentum of a system remains constant unless acted on by an external source. So, conservation of angular momentum is the rotation of linear momentum. So let's get the equation for angular momentum. The equation for angular momentum is L equals I times W. The L is the angular momentum. The I is the moment of inertia. And W is the omega, or the angular velocity. This equation is from the equation of linear momentum. The equation for linear momentum is P equals M times V. P is the linear momentum, M is for the mass, V is for the velocity. So we know about the conservation of angular momentum. Now let's have an example. This is the example. What is the angular momentum around the catcher of a baseball thrown at 40 meters per second? The weight of the baseball is 145 grams, and on a wild pitch, the catcher has extended his arm 1.25 meters from the center of rotation. So this is the example question. We have the equation angular momentum equals I times W. But we cannot solve this equation because we need the formula for linear equation. P equals M times P. Substitute this from this. We have the equation L times mass, L equals mass, radius, and velocity. Now, let's move on to this example. The given is, for the mass is 145 grams. The radius is 1.25 meter, and the velocity is 40 meters per second. The angular momentum is 6. For this to solve this example, we need to convert this to kilograms. Because the unit for angular momentum is kilogram meter squared per second. So let's solve this example. L equals 0.145 kilogram. This is the convert of this times 1.25 meter for the radius and 40 meters per second for the velocity. Let's solve it. 1.145 times 1.25 meter times 40 meters per second. The answer is, the angular momentum is 7.25 kilogram meter squared per second. So that's all for the angular momentum.
Hello, everybody. I'm Jeremy Nabasa, and I'm going to explain about the rotational motion of inertia, or commonly known as moment of inertia. First, we will define what is the meaning of rotational motion of inertia. Rotational motion of inertia means that determines the torque needed for the desired angular acceleration. Torque needed for the angular acceleration. It depends on the body's mass distribution is axis to larger moments requiring more torque to change the body's rotation. Then the rotational motion of inertia also plays the role in rotational kinetics that plays in linear kinetics. Rotational motion of inertia characterize the resistance of a body changes in the motion. And the rotational motion of inertia depends on how mass is distributed around an axis of rotation and it will vary depending on the chosen axis. Here's one formula that can be used on the rotational motion of inertia. D squared. This formula can be used on the thing that pointed like mass, and V is the distance and N the mass. This is a point like mass. And for an extended body, the formula is just the moment of inertia is just the sum of all the small pieces of mass multiplied by the square of their distances from the axis in question. Rotational motion of inertia can be measured by simple pendulum, because the resistance to the rotation is caused by gravity. This is a sample problem for a rotational motion of inertia. The moment of inertia or rotational motion of inertia of an oxygen molecule is about an axis draws the center of mass and perpendicular to the line joining the atoms is 1.95 times 10 to the negative 46 power kilogram meter squared. The mass of an oxygen atom is 2.66 times 10 is to the negative 26 kilogram. What is the distance between the atoms? And with the given I is the angular velocity. And this is the angular velocity. 26 kilogram meter squared. And N is the 2.66 for the mass, then negative 26 kilogram. And we will find the distance between the atoms or the angular velocity. Yes. The formula for this is 2 times I over N, or mass. And we will just substitute the value of the given variable. Square root of 2 times 1.95 times 10 raised to negative 46 kilogram and squared, and over 2.66 times 10 raised to negative 56 kilogram. Sorry. Multiply this and the answer will be 1.21 times 10 negative 10. Just cancel this, and square of the answer of this is this, and the angular is the answer of the distance between the atoms is 1.21 times 10 to the negative 10 Newton, and that's